It's a great pleasure to speak here. So this is a little bit of a switch of gears after a very conceptual morning. I became interested in the question of extracting entanglement and its energy cost after I had in general studied entanglement properties of relativistic fields in space-time, and also during my PhD the entanglement in loop quantum gravity of spin networks. So what I'm looking at here is a very general scenario where I ask the question, if we consider a system that has a quantum state that is highly entangled, for example, the state of a quantum field, a bosonic or fermionic field, but also space-time itself, if it's a quantum state, or some other large systems, such as a condensed matter system, that we can couple to. If we want to access this entanglement, what do we need to pay in energy? And for that, I consider a very simple scenario. So let me get started. We all know that entanglement is a hallmark of quantum theory, but that it's also a resource for a large number of applications in quantum information. And just to give the classical examples, we have superdense coding, quantum cryptography, quantum teleportation. But all of these applications require that the parties involved in such a protocol, often referred to as Alice and Bob, actually have access to this resource so that they share an entangled state. And of course, we know that ground states of field theories with local Hamiltonians, or in general, quantum systems with local Hamiltonians that have some interactions, so are not ultra-local, that they are spatially highly entangled. Not volume law, but area law. And the question that I'm posing here is, if we utilize this entanglement by having two local parties in, for instance, a spatial slice, coupling to this entangled state, in order to extract a part of this entanglement, how much do they need to pay in energy? So if we want to extract an amount delta S of, so here I use entanglement entropy, then we will necessarily change the state of the system. If we start in the ground state, after having extracted entanglement, clearly we will not be in the ground state anymore. And thus, we will have increase of energy that we need to pay for within our protocol of extracting entanglement.
Is it obvious you cannot do it for free? Pretty obvious, or
yes. Yeah, it just follows from the fact that the state will be different. If there's a unique ground state.
Just get something out of it without changing it? Is it not obviously not possible?
No, because I mean, you extract correlations. If you're, but I guess you can argue that based on monogamy of entanglement. But I would say, yeah, there's no way to couple to an entangled state and suddenly get something entangled without changing the state. Yes.
It's reasonable. I just
can't
see it immediately.
Okay. Okay, so that's the question of this talk. What is the minimal price in energy that you need to pay to extract entanglement? And that's a difficult question. So there are several steps of kind of simplifying the problem so that I can actually attack it. So I will draw something here just to talk a little bit about the setup. So if we think most generally, we have somehow our large system.
Can I ask you a question of clarification? This
Yes.
energy is energy only of the field, or it's an energy also of the detectors?
So I'm interested in getting an estimate of the minimal energy cost. And so that means, like, I'm interested in finding a minimum of the energy, which it might not necessarily be the optimal minimum. I want to find a lower bound. And so for that purpose, I will ignore the energy cost in the system and even in the procedure. So there I will focus really on the energy cost that you need to pay into the system. But
System is the field alone.
is the field alone, yes. But you're absolutely right that a more elaborate consideration also will need to include how much you need to pay in the procedure and so on. Yeah.
Sorry, for the general state, you wouldn't be able to extract entanglement without energy.
Oh, that is absolutely right. If you do not have a unique ground state, there is a subtlety where you might be able to extract energy without paying something for it. That's right. And that's actually also something that we will find in the end, that if you have a degenerate spectrum, degenerate ground state, or states that are kind of continuously connected, so a gapless Hamiltonian, that you might be able to do it for free.
So it's not so obvious that there is a cost.
If the ground, okay, absolutely. If the ground state is not unique, then you could change it to a different ground state and possibly extract entanglement there. So we have a large system in which we have a state psi, and we consider a subsystem A that is local and a subsystem B that is only allowed to couple locally. And then we have somehow the rest of the system, which is essentially the full system, maybe I call it V, without A joined B. Now, clearly, the restriction of the state psi will lead in each region to a density operator that is in general a mixed state, B, and then in the rest rho C. And in general, we will have entanglement between all of these pieces. So A will be entangled with the rest and share some entanglement with B, and so on. Now, a big simplification that I will use for the following computation is to say, well, if we ask for the minimal energy cost between A and B, we could simplify the problem by making B very, very large, such that B actually becomes C. Because obviously, in order to extract entanglement between A and B, even if B is smaller, the energy cost by putting additional restriction on B, by localizing it in space-time or space, will necessarily increase the energy cost. No? If we loosen the conditions to the problem, it will be easier. Of course, that will mean that the results I will be obtaining this way will be subject to less constraints, but they will still be a valid lower bound. And that's what I will be considering in the following. And the next step, to then put additional restrictions on locality, is something that I will discuss in the end, and that is a next step. Okay, so the setup is the following. We have a bosonic or fermionic field theory with a quadratic Hamiltonian. So in general, we have some integral over some spatial slice of some position-dependent matrix that describes coupling of the bosonic and fermionic fields that we consider. And an example would be a Klein-Gordon field or Dirac field, which could be in Minkowski space or also a general curved background. However, as I would like to have at least for that time interval under consideration, a ground state, at least for the in the regime where I consider that I want to have time-independent Hamiltonian. So I want to have some kind of stationary system where I can consider the ground state of this Hamiltonian. Now I choose this subsystem A, Alice, and I make it as small as I can choose, because I can always then look at larger subsystems by putting several subsystems together. So the smallest possible subsystem for such a bosonic or fermionic field theory or bosonic fermionic system is a single mode. So mathematically, we have some Q and P corresponding to some smearing of the fields that have canonical commutation or anti-commutation relations. So that represents a single bosonic or fermionic degree of freedom. And through this smearing, I essentially choose, for instance, some local subregion in which this subsystem is defined. Yeah.
So psi necessarily defines observable?
It is true that they are, well, okay, there are two ways to think of them. Yes, if they are Hermitian operators, they would be essentially field operators or conjugate momentum operators, so linear observables of your field. You could also allow, I mean, you could do a basis transformation where you allow complex combination, and you could think of them as creation annihilation operators, and then they wouldn't be. But exactly. Yeah.
This is confused by notation. I think psi is not the field in the sense of standard field theory. It's
So for Klein-Gordon, you can think of psi of x as being two components per spatial point, which is phi of x
and p of x
and pi of x. Exactly.
Yeah.
But you could have more degrees of freedom and so on. And now there's an important result that I will be using, and that is that every choice of such a mode has a unique partner mode that is also such a smearing, which is the partner that has maximal entanglement with the first mode. And of course, this is with respect to the state under consideration. Yeah? So every state and choice of a subsystem defines a unique partner that is maximally entangled. And that also means that if I now want to use any protocol of extracting entanglement, it actually suffices to look at the extraction of entanglement between A and its partner. Because if I would consider extraction between A and any other mode in the system, I will only be able to extract from that part in this other mode that has overlap with the partner. And of course, in that case, I will also change the most efficient way to change the state during an extraction protocol is to only modify that part that actually has entanglement. So that simplifies the problem tremendously, because we can now reduce the system to just the consideration of a chosen mode and its partner. And the corresponding field state will be a tensor product between a pure state, but entangled, between A and its partner, and the rest. And so any protocol that has the goal to extract at the minimal amount of entanglement, of course, should not touch the rest. So I can really think of coupling to A and Alice coupling to A, Bob coupling to its partner, and then performing the extraction protocol. However, I should say that with this picture here at the beginning, in general, if we have a localized mode A in some region, its partner will be typically very delocalized. And that's what I said at the beginning. I mean, actually implementing this protocol for the purpose of having two local parties, Alice and Bob, will not be possible. So there we will see that the actual energy cost will be larger than what I'll be deriving here. Yeah. Okay. So let me tell you the protocol. So we start with this state. Alice couples to mode A, Bob couples to the partner, and we assume that Alice and Bob start off without having entanglement. So we have a state for Alice and for Bob, and now our extraction protocol is to perform local unitary operations such that these states just become swapped, which you can do by local interactions with mode A and mode B. And the resulting change is that now Alice and Bob share the entanglement in here. but the energy is increased by an amount delta E. So the question is, what is the minimal delta E to extract this amount of entanglement? And that's the result. So this is the consideration for bosons, and that's for fermions. And the only property of the system that the result depends on is the spectrum of the field theory Hamiltonian. Namely, the smallest two energy eigenvalues. So that means if we have a field theory that is massive, then of course the smallest excitation energy, the excitation spectrum of this Hamiltonian will correspond exactly to the mass of the theory. In general, if we have for instance, a Bose condensate, you will find some other spectrum, but essentially you will look at the Hamiltonian, compute its spectrum, and the first two excitation energies will define the scale at which you pay the price. And what I'm plotting here is assuming that the first two eigenvalues are the same, the spectra, then that one is 10 times as large as the other, and then that the second excitation energy goes to infinity with respect to the first. And we see that even in such a scenario, the energy cost per entanglement extraction is finite. And we see here, if I want to extract an amount of delta S of entanglement entropy, then I will need to pay at least this amount, like above this line. For fermions, for bosons, we see that this cost increases exponentially with the amount of entanglement. Well, for fermions, there is an interesting scenario. Yeah. So there is a maximal amount of energy, and if the two energies are different, one even sees that one already needs to pay the maximal price at a finite amount of entanglement. And so once you have reached that, in that case, you can directly also extract the full amount of entanglement because it doesn't get more expensive.
So one quick clarification about the framework.
Yes.
So did you fix the two regions, or you fix one, find the partner mode, and then focus on that?
Okay, I can very briefly tell you how this was derived.
Yeah.
So, but it's really what is the minimal cost of extracting entanglement from the system. So that also means that we optimized over all ways to choose a mode and its partner. So let me very quickly go, just to give an illustration. So the way we derived it is by assuming that we already solved the problem. It's a very good way to start with. So we assume that we have already found the optimal modes A and its partner. And then we can forget about the rest because we can just study the properties of the subsystem. So we have a Hamiltonian now just with 2 degrees of freedom that necessarily, one can show that, is given by a quadratic Hamiltonian with a ground state given by psi A bar. But these 2 decoupled degrees of freedom, Q1 and Q2, they will, of course, not be corresponding to the subsystems A and A bar, because those are entangled, while the ground state of this Hamiltonian is clearly a product state of the ground state of this times the ground state of this. So what we want to find is somehow the transformation between these degrees of freedom, or these modes, and the modes that are actually entangled. And for the derivation, one can even simplify that these energies are the same, the excitation energies of these 2 modes. And we can then just optimize in the system to find the optimal ways to choose A and A bar in it that have exactly the entanglement that we want to extract, and then compute how much it costs. And this will, of course, depend on the energy excitations of these 2 degrees of freedom in the choice. And then we can ask, what is the optimal choice that this, because we assume that this is already the solution, how this is embedded in the full system where we have an infinite number of modes. And to then derive this expression for bosons, we can compute the entanglement entropy from a squeezing parameter. One can then go to transform from Q1 and Q2 to QA and QB, and can show that the Hamiltonian that I showed here takes this form, so that we have an interaction term that in the entangled ground state lowers the energy. And so if we cut off the entanglement between system A and system B, mode and its partner, because we extracted this entanglement, then we won't subtract this piece anymore. And so the energy will be raised. And the energies of these individual Hamiltonians, they have the energy in it and are exponentially large in the squeezing parameter that also describes the entanglement entropy. And that means from that we get a price of energy. And even if the parameters epsilon1 and epsilon2 are different, we find a slightly more complicated formula for the energy cost. And then you optimize, and you find that, of course, as this is monotonic in epsilon1 and epsilon2, that the optimal choice is to go to the minimum of the spectrum of your Hamiltonian. So let me summarize. We could derive for both bosonic and fermionic quadratic systems the minimal cost of entanglement extraction between a single mode and another mode. That, of course, is optimal if you choose a single mode and its partner. But it is a lower bound also for any other methods. And of course, we would like to tighten this by now, in the next step, to look at more general scenarios where you restrict further what type of subsystems you're allowed to choose. Thank you very much.
Okay, so really late. Let's have two quick questions.
So indeed, I was interested in interacting systems or perturbations. Do you already have any intuition of that, or is there any preliminary studies that the costs, I guess, will change because the entanglement structure changes? Is it getting more expensive, or is it?
As far as we understand, and there is a little bit of work that kind of built some toy systems where they still find for bosonic systems the same exponential growth, that the cost per entanglement that you extract grows exponentially with the amount of entanglement entropy that you extract, but the coefficient is different. But I don't. Yeah, it's yeah.
Else. I guess it's very hard to go beyond that.
In that work, they make some more general. I mean, they claim that at least this exponential behavior should be relatively general, but they are more arguments rather than proofs. And we essentially worked out for the simpler case a rigorous result. So that's kind of the trade-off. Yeah.
Okay, one more question. There's nobody else.
This is maybe stupid to take. Why is epsilon 2 relevant? It seems after what you've said, tell me what is wrong. You're just working with a ground state, the first excited state. You have a two-level system. You use that as your two-dimensional Hilbert space, and you do your little game in that space, and that's the result turned out to depend only epsilon 1 and epsilon 2. Well, that's wrong because it does become some epsilon 2.
Because those two states don't necessarily have the entanglement structure to, I mean.
But if you couple to linear combination of these two states, you do or not. Or maybe that's not true. It's near, but what I said is nearly right, but it's wrong. So, suppose this, your field only have these two states, nothing else. Couldn't you do the same game and only use an energy epsilon 1?
maybe by changing the protocol in the sense, I mean, that we had these assumptions of coupling to individual modes because we wanted to have the tensor product structure.
I couldn't expand any more than this.
That's right, yeah. So, would be...
Maybe then I can lower it.
If you change the protocol, you might be able to get only the energy difference between the first excited states. I think I would need to think how to put the protocol, but I mean, then of course it also becomes highly dependent on how these states are actually constructed, how they lie within the tensor product structure of your theory, which I kind of here circumvented by just using the standard tensor product structure that is given by locality or Fourier transform, essentially by Fock space. Yeah. Okay, thanks.